sure it's online. Okay, good. Okay. Hi everybody. I hope you're staying safe at home, being careful. And as I said, I'm gonna be writing code to solve a programming challenge. I get it in my mailbox all the time because I'm apparently a sucker for punishment. And I like to play around with them. So let's see how it works. Sorry about that. So represent an integer in a linked list format by having each node represent a digit in the number. So it's from the singles, right? This is a single digit, this is 10 digit, right? Because 1, 2, 3, 4, 5 is a number 5, 4, 3, 2, 1, right? 1, the first thing corresponds to the single digits, 10 digits, 100 digits, thousands, tens of thousands, right? And if we have 99 plus 25, right? Because remember, this is written kind of like in the reverse of what you would naively expect, right? So this is 5 plus 20, so 25, plus 99, which is 124, which is 421. Okay, so let's go ahead and start doing that. And I guess first we want to have a class number is list, and there's different ways to do that, but let's kind of like so you have import utter, right? So and I'm gonna like and since numbers can't change, right, just like in Python, but make it a frozen class, right? It's always kind of nicer. And oops, that was number as list, and basically oh, I don't need to write it in it because I already have that. So what we do is this is gonna be a bit annoying, but I think that's the best. I'm not gonna bore you too much with like modern typing. Maybe later we can get into that. But digit, and that's gonna be an int, and I guess rest, and that's gonna be, we'll put it as any, this number is a list. And now let's do add class method. This is just a convenience that will be useful later. From number, if I was doing it in a real integer, I wouldn't be bothering with that, but this is kind of fun, so why don't I show you that number, and we'll write it recursively. Later we can talk about how we would eliminate the recursion, but for now let's do this. So and I wonder how many people know about this thing, right? So let's kind of like I want to show you something. If you have, say, 15, no, let's say 25, right? One of the examples here, and we do div mod 10, we get 2, which is how much you would divide 25 by 10, right, on the integer part, and 5, which is a remainder. So we can do literally digit comma rest equals div mod number 10, and we do if I guess first we want to do something like that. If this is actually pretty cool, right? If number, I kind of want, well, what does it mean to have an empty list, right? So I'm just gonna represent like the empty linked list with none. So if number is 0, I'm just gonna return none, which is one of the nice things about having a class method as a constructor, not a real constructor, is that it doesn't really have to return an instance of number as this, right? There's no rule saying that In this case, it does make it more sense to just return none. And digit rest equals digit mod number 10. And no, this is no opposite. This is rest comma digit, and then we do rest equals number the right thing is CLS phone number rest, and then return CLS digit equals digit, rest equals rest, and we can easily debug that, right? So let's put the debugging here. Let's do number as list dot from number 54321. Whoops. Rest equals rest, not comma rest. Okay, so that's a silly mistake. We can fix it easily. And as you can see, it's a linked list, right? It's one, and then and we can maybe have like a nice str. So let's see, utter str. So we can have kind of a cool string. So I want to see how we disable the under str. Here, str equals false. Okay, good. That's pretty easy. Let's do this str. And let's implement under str ourselves. Right, so we still have wrapper to kind of do the real thing, but let's write str. And again, like the only reasonable way to do it is recursively. So let's do this. Return f digit. And here I do want to do something interesting. So it's a little bit of a cheat, but that's fine. If rest is none, right? So you see that kind of here in the representation here, right? You didn't have 2 going to none, and you really should, right? Otherwise it's not a real linked list, right? Like how do you say that it stops here, right? You do have a pointer to none, but it's kind of nice to hide it in the informal representation. So we check if self.rest is none. And again, this is kind of just fancying up like the infrastructure to kind of make the output a bit nicer. If it was really kind of like under a time crunch, I wouldn't be str of self digit, and otherwise self digit and self rest, and this is implicitly called str, right? So that's kind of cool. We don't even need to worry about calling it explicitly, and I think that should just work. So we already have the wrapper, so I'm gonna delete that. And now if I want to do print number as list dot from number of 54321, just like in the example, you see that it's kind of cool, right? We have exactly that. And you notice we don't need the converter the other way, so that's fine. It might be kind of fun to write it later, but let's and I'm gonna say something about fun and write it later. So hopefully I remember that. Let's see if I remember that. But okay. So now let's do add number as list, and no, summon 1, summon 2, and first we'll do kind of the edge cases, right? So if summon 1 is none, right? If you're trying to add 0 to something, then you just return the other one, right? So return summon 2, and vice versa. If summoned 2 is none, and some people would do an elif, but I think it's silly because you have the return, right? You don't need to do elif. And if you don't have the if elif, then the nice thing is that like the normal case, let's return not with -1. And the nice thing is, the normal case, it can be completely unindented, right? So we have kind of more space, which is kind of nice, right? Especially I increased the font to 150% here, so so that I don't have too much space for extra tabbing, so every indentation level, you know, kind of really hurts. So let's try to conserve indentation level. So now we do this. Let's do here remainder. Do so if summoned one is none. First, let's do kind of like the real edge cases. Both of these are none. If summon one is none and summon two is none, and we'll kind of give remainder default of 0. This way, we don't have to worry about like. And maybe we'll kind of play around with it later. Let's see. If summon one is 1 and summon 2 is 1, right? If both of them are 0, then it's easy. We will just return number as list of remainder and none. Right? So in this case, we just, you know, we only have one digit, right? So now, if summoned one is none or summoned two is none, then now we know that at least one of them is none, and so we can do kind of all kinds of tricks, but we can take advantage of the fact that should actually do that kind of explicitly here. We could have done other stuff, but let's kind of explicitly do this. So you notice that we never have 0 here, right? You know, like if it's correctly done, right? Maybe we could just do this. Return we can just assume that it's true for now, and we can kind of deal with other corner cases later. Okay, so then we can know that like so we grab whichever one of them is not none. So we can just kind of like move the remainder to the other one, right? So we can do return add null summoned one we might be able to merge these things. We'll see later. But I don't need that line anymore, so let's kill it. Okay, number is this reminder, and this is obviously 0, so we basically just again moving to a case where both of them are not none, right? Because a remainder and none, right? So it's just adding it one digit number. So I know that both of them are not none, right? So let's do kind of like, you know, singles equals summoned 1 plus summoned 2. But you will notice that singles can be bigger than 10, right? So we actually want div mod ten new remainder single equals div mod, right? Div mod is going to be very useful throughout this exercise. And then we do return, and then we do this, we do rest equals add null. So remember that both of them are not null, right? So I can do summoned 1 dot rest, summoned 2 dot rest, and this is kind of why I wanted to move to like a common case, right? So this is a classic trick of harmonizing. Actually, like this is, we don't have to call. Let's do this. And we test it, we'll test like the corner cases first because that's always a good idea. Summon to close. Loop, 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 and remainder equals 0, right? So we basically move the remainder, and we don't need an extra return statement. Here we go. I think that's good. And now obviously both have rest. Rest might be none, but it's still a rest. Okay, so this is good. And now return number as list and do summoned one singles and rest. Right, and these algorithms are like it's always possible to turn the recursion here into iteration, but let's kind of do it like this, kind of see how it works. Okay, so now let's kind of start testing now. Okay, so let's do this. Number as list, one, none. That should be one, right? Let's do from number. Let's actually start by adding 0 and 0, right? So add 0 and 0. And you know, especially if I print it, it's kind of obvious to see what's going on here. Actually, this is wrong. So we should probably take care of this aspect. If remainder is 0, return none. In other words, okay, so this is like the real corner case. Let's evaluate it. The real corner case is that it's none, right? Which is how we represent 0. Okay, so now if we add 0, 0 with a remainder of 3, we get 3. If we add, let's not replace them. Let's kind of do separate things, okay? So we can kind of actually see all the cases. I think it's going to be fun, and we will kind of look at the code later again. So now we want like another 0 remainder. Okay, that does what we expect. And now we do number as list from number, let's see, 1. Again, this is an empty remainder. Let's start that. Oppa. Oh, because this should not be plus, this should be calling number, not add. Yes, that was a silly mistake. Here we go. Maybe later we can kind of like do an operator, but it's fine. Let's do it like that. Okay, cool. Okay, so these cases still work. Oppa. Because it's not called add, it's called add now. Okay, bloop, 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 bloop. Oop. And summoned one dot rest. No, oh, that's not what I want to do. I want to summoned one dot digit. This should have been a real, okay, that's what I want. Dot digit. Sorry about that. That's the kind of mistakes you make when you start writing code. Okay, I think this should be good. Okay, cool. Yeah, no, that looks much better. Okay, this is still none. This is still none. Okay, 1 plus 0 with 0 remainder is 0. Now let's do it the other way around just to check that our addition is still commutative. Bloop. Beautiful. Let's check what happens when we give it a non-zero remainder here and a non-zero remainder here. Kind of just carefully checking all my base cases, because if you don't have the base cases covered, then nothing else will work. Okay, so yes, 1 plus 3 equals 4. All good, like so. Single digits seem to work. Now let's kind of do a more complicated, still single digit, by the way. Like there's still a lot to test with single digits. So what happens there? That should be 12, right? Up. Yep, 2, 1. Good. So we kind of got 6 plus 6. Okay. And again, I want to kind of make sure I have all my bases covered. So let's do this. And I think this covers all the cases where, like, I you know, one of them is not, right? So let's start adding two numbers. So let's start by adding 3 plus 4. And if I was writing real code, maybe I would actually do unit tests here, but I actually think that this is kind of fun to just print them out and kind of see how it goes, right? Clearly, like if this was production, right? Okay, so and let's give it a remainder. So 3 plus 4 plus 2 is 9. And if we add a remainder that's a bit too big, say 3, we get 10, right? So 0, 1, that's 10. Okay, and I think by now we can just, like try 99, 25. And if you're wondering why I need the remainder at all, it's because even if you don't use it in the original call, right, you see that I have the new remainder here, and that can be now 0. So I always can have a remainder even if I didn't start out with one. So it's kind of convenient to do it equal to 0 at the beginning. And 124 is expected. And I think this kind of like, is a case that's probably interesting enough that I couldn't have made serious bugs here without writing the code. So that's kind of cool. And I want to show you one more thing. Right, we can easily turn these things into integers, right? Again, like the same recursion. We can do this, return self.digit plus 10 times if self.rest is none, return self.digit, otherwise 10 plus int of, or we can just do this, or 0, which means self-rest is none, will automatically have that, so that's pretty cool. And now let's kind of do this, right? So let's do x equals this, right? And if we look at x, it's 124. But if we turn x into an integer, and we also turn it into a string, you'll see that it's 124, represent like that. Okay, so here's another way to implement add null. So let's do this. Def add null to the easy way. And we can talk about why, like, you might not want to annoy people doing that, but you also are watching me, so I can so we can do this. Int of summand 1, int of summand 2, and let's see if it works. Right, so we got the right answer, right? It's 124, same as Edna. And what's going on here, right? Like Python already knows how to add, right? We can just convert them to integers, and nothing in the rulebook says that dog can play basketball, and also nothing in the rulebook says we don't have to do that, right? Like this, nothing here says it that we can't do that. So then, if you get an annoying interview, oh, what if the numbers are really big? How big do you want me to make them? So basically, they'll probably tell you, okay, let's do like ah, this. Sorry, that's what I meant to do. Forks, right? Like big enough for you? You want Google? I'll give you Google. I'll give you Google. No worries. It's kind of hard to read, but you can count them or debug it some other way. It doesn't matter, right? Because we don't have to print them. But if we didn't print it, would be really, really long, and that would be annoying. But it's just annoying us, right? The computer's fine. It did it fast. It did it actually faster than it probably would have done it. And that's because Python supports big nums, right? So I can put, like the output is going to be starting really long, right? So okay, you want Google squared? To add it to Google squared? Oh, yeah, Google squared. It's, to Google squared, right? And if you do like, plus 5 here, and say plus 15 here, you get, 2 Google and 2 Google squared plus 20. Right, and if you do 3, then you'll get 2 Google squared plus 18, right? Like the limit is like how much patience I have writing the inputs, not the code, right? The code will do whatever I tell it to do. So, and again, like to be clear, this is no different than add null, right? So if I do without the easy way, it will still work the same way, right? I guess you can either trust me or verify yourself after this that these are actually the same number, right? And the same number of zeros. It works, right? And that's because Python supports big nums. Clearly, this is not the intent of the question. The intent of the question is to figure out so how you handle it in an actual kind of interview. You depend on whether you like my series of tweet posts with the interviewer yelling at you to get out. Ideally, the interviewer will not literally yell at you to get out, but some people get upset with all kind of things. So you might want to kind of mention, look, I could have done this, but clearly I'm guessing that you actually want me to write the algorithm itself. Blah blah. You can play around with figuring out exactly how to answer. But this is kind of cool, right? Like this is kind of the advantage of kind of having implemented this as a nice class that I can add method that I actually have an int. I started implementing for number mostly as a convenience, but now that I've done that, I could implement it as like this like super simple code, right? And you might think that like I'm kind of cheating because I hid a lot of code, but look, this is 2 lines of code. This is like 4. This is, even if you kind of put in the method, it's less code than what I had here. And this code is a lot more complicated, right? Like here I had barely one if, and this if was pretty simple. Here I have a couple of nested ifs and then another if, and I have to use an or here, which is kind of an implicit if. Like lots of cool tricks to kind of avoid complicated code. Even with all these tricks, it's still 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 lines. And here, even if you add the cost of both of these lines together, it's 1, 2, 3, 4, 5, 6. And the code here is simple. Yes, there's like a little or here. It's not completely trivial, but it's way simpler than this, right? Because like where I hid that complexity is in the Python C code, right? The Python C code works really hard to give you this, right? And again, like, like don't worry about this right now, right? Like the thing is that, like, if we don't do all of these, weird things, right? And if we just, okay, let's just look at the numbers, right? Like, I want to, add Python numbers, right? So if you look at kind of like what's going on here in this code, not here. Let me go up because it's like shift. Okay, here we go. Just this is kind of subtle, but yes, if I want to add these two numbers, right, it works, right? It's like literally the same. The only difference is the representation. But the thing is that Python has to work really hard for that. There's a lot of code in the C Python implementation implementing big nums to make sure that this works, right? This is not trivial, right? It looks trivial because it just plus here, but plus in Python hides a lot of complexity. It's not like a backend into an assembly instruction like it is in C, right? So the complexity that I can avoid here by writing this code and then kind of like having to convert to and from numbers is because Python is a pretty sophisticated language, right? And the original question didn't mention Python, right? Like they can ask you to do it in C, right? And if you look at the code in C, look more or less the things, right? You can kind of translate it bit for bit, and like you would kind of see the translation working. But like you wouldn't be able to do this trick, right? You'd have to use some library like JP2, and then they would say, oh, no external libraries. But I didn't have to cheat with external libraries. Sure, I used Atos, but Atos didn't give me a lot of power here. I could have implemented an init, right? The problem is not that they don't know how to implement an init and a wrapper, right? Like it's kind of nice, and I have the frozen equals true, which is kind of nice to make sure that nobody can change a number. But again, it's not essential. I could have avoided using Atos, and I could have avoided using typing. So I didn't have to use an external library here to kind of get this, right? This is the power here does not count on the fact that I use Atos. The power here, right? Sorry, the power here, right? The power here is not from the fact that I use Atos. The power here is from the fact that Python has a built-in addition of big nums, right? The class that Python calls int is a big num, right? Look, it can represent Google squared, right? Google squared does not fit in a 32-bit int. It does not fit in a 64-bit int, right? If you want to see, let's check very quickly, right? Wait, we can compare because it actually implements right, and you can even like do this, right? It's gonna be a pretty big number, so bear with me, but you can even check exactly how much bigger it is. The answer is a lot bigger, right? It's like most of it, right? It's like this is really small compared to this, right? So even if you have a pretty big computer word, you're not gonna get a lot, right? There's still lots of nines in these numbers, right? So my point is that the class that Python calls an int here we go. The class that Python calls an int is an integer in the mathematical sense. It's okay to call it int, but it's not an int in the CPU sense, right? It's not a 32-bit or a 64-bit. Usually we would call this thing a big num. And like it doesn't even kind of like make itself sound really impressive by that, but it is pretty impressive that int can represent any integer, not just things that fit in a CPU word. And I guess that will be my if I managed to tell you anything interesting, hopefully that was kind of an interesting. And if you saw my my talk about numbers in Python, or hopefully the video will be up soon. They told me around August, so we're already in July. So you'll see that I write very depressing things about numbers in Python, but this is a pretty awesome thing. So maybe I can compensate for making people sad by making people happy again. And I guess what more can I hope for than to make people happy? And with that, I'll say bye bye, and I hope you enjoyed this.